15 minutes. That is the only second warning you get. Not an aftershock, not a fault rupture, nothing on any seismograph that would normally explain what happens next. 15 minutes after the ground stops moving, something else arrives, and for 15 years, nobody knew what it was. The data sat buried in GPS logs, flagged as an anomaly, filed away and forgotten, until one geophysicist at the University of Chicago decided she was not going to let it go. What she found rewrites what an earthquake is physically capable of doing. Not at the surface, not at the fault line, deep inside the earth, at the boundary between rock and liquid metal, at temperatures hotter than the surface of the sun. By the end of this video, you are going to understand what a second shockwave is, not as a theory, not as a simulation, as a measured, confirmed event that moved an entire country without a single seismograph registering a cause. You're going to understand why every earthquake risk model currently in use is built on an assumption that Japan just proved wrong. And you are going to understand why scientists now believe this has been happening for over 100 years. In Chile, in Sumatra, in every region that ever produced a magnitude 9 event without anyone ever knowing. Because they did not have Japan's instruments, and we are only starting to understand what we have been missing. Start with March 11th, 2011. A magnitude 9.0 earthquake struck off the coast of Tohoku, Japan, one of the 5 most powerful earthquakes ever recorded by modern instruments. The shaking lasted approximately 6 minutes. Tsunami warnings went out within 3 minutes of the first rupture. The wave reached the coast in some areas in under 30 minutes. The death toll exceeded 19,000 people. The damage exceeded $200 billion. Seismologists around the world had their instruments running. Japan has one of the densest GPS monitoring networks on the planet. Hundreds of stations distributed across the full length of the archipelago, from the northern island of Hokkaido all the way down to Kyushu in the south. 16 minutes after the shaking stopped, every single GPS station across Japan simultaneously shifted eastward by 5 to 6 millimeters. Not one region, not the area near the epicenter, every station, across 1,800 miles of Japanese territory, moving the same direction, at the same instant. No aftershock was recorded at that moment, no fault rupture, no pressure wave registered on surface seismometers, nothing that should have been able to move an entire country 16 minutes after the earthquake ended. The scientists logged it, they noted it, they had no explanation for it, and for 15 years it sat in the data. Sun-Young Park was a geophysicist at the University of Chicago. She was not looking for anomalies. She was working on a different problem entirely when she encountered the Japan GPS data and noticed the shift. It did not match anything in the standard earthquake model. It did not match aftershock propagation. It did not match surface wave behavior. It did not match any known mechanism for post-seismic deformation at that scale and that timing. She went back to the physics. Not the surface physics, the deep earth physics. What actually happens to seismic energy when it travels downward instead of outward? Here is what most earthquake coverage never explains. When a fault ruptures, energy does not only travel outward across the surface the way you might imagine, a ripple spreading from a stone dropped in water. Energy also travels downward, straight down into the earth, through layers of increasingly dense, increasingly hot rock, down through the crust, down through the upper mantle, down into the lower mantle, all the way to one of the most dramatic boundaries in planetary science, the core mantle boundary, the point where solid silicate rock meets liquid iron and nickel, where temperatures reach 4,000 degrees Celsius, hotter than the surface of the sun, where pressures reach 1.4 million times what you experience standing at sea level. That boundary is not an abstraction. It is a physical discontinuity, a surface, and like any surface, a wall, a mirror, the floor of a swimming pool, it reflects energy that strikes it at the right angle. Seismologists had known about core reflections for decades. They had detected faint signals bouncing off the core mantle boundary in the aftermath of large earthquakes. They had modeled the travel times. They had confirmed the basic physics. The assumption, the universal assumption shared across every major seismology research group, was that the energy would be too dissipated by the time it completed that round trip to do anything meaningful at the surface. 3,600 miles down, 3,600 miles back up, through 2,700 miles of mantle, through temperature gradients and pressure gradients that should bleed the wave of nearly all its coherent energy. The assumption was that by the time a core reflected wave arrived back at the surface, it would be a whisper, detectable by sensitive instruments maybe, capable of triggering fault slip, capable of moving a country. Impossible. Japan proved that assumption wrong. What Sun-Young Park and her team confirmed, published in 2026, is that the 5 to 6 millimeter GPS shift recorded 16 minutes after the Tohoku earthquake was not caused by the original earthquake. It was caused by an echo of it, a wave of seismic energy that had traveled 1,800 miles straight down from the rupture into the earth, struck the core mantle boundary, reflected back upward with enough coherent force to travel 1,800 miles back to the surface, a 3,600-mile round trip, completed in approximately 15 minutes. When that wave arrived back at the surface, it did not just register on instruments. It still carried enough force to trigger fresh slip on 4 separate tectonic plate boundaries, including 2 that the original earthquake had never directly ruptured. The total energy released by this delayed pulse was equivalent to a magnitude 7.5 earthquake. To put that in perspective, a magnitude 7.5 event kills people. It destroys buildings. It reshapes coastlines. This was a second earthquake, triggered by a wave no one was tracking, arriving 15 minutes after everyone assumed the danger had passed. It moved an entire country. Again. Now, understand what this means for the model. Every earthquake risk framework currently used by governments, insurance companies, and emergency management agencies is built on a core assumption. Once the main shaking stops, the immediate threat from that specific event begins to decline. Aftershocks are modeled separately. Tsunamis are tracked as a consequence of the initial rupture. Secondary hazards are calculated based on slope instability, liquefaction, structural damage from the primary event. None of those models include a variable for a core reflected pulse arriving 15 minutes later with the energy of a magnitude 7.5 earthquake, capable of triggering fault slip on plate boundaries the original rupture never touched. That variable does not exist in the current risk architecture, because until Park's paper, there was no confirmed evidence that the variable was real. Now there is, and the implications cascade outward in ways that are only beginning to be mapped. Consider the geometry of this problem. The core reflected wave from the Tohoku earthquake did not arrive back at the epicenter. The physics of deep reflection mean the energy spreads across the surface in a ring, arriving first at intermediate distances, then at greater distances, depending on the original rupture geometry. This is why 4 separate plate boundaries experienced fresh slip, not a random cluster near the epicenter. 4 geographically dispersed boundaries, each one sitting in the zone where the reflected wave arrived with sufficient amplitude to push a locked fault past its threshold. Scientists do not yet know how to predict which faults will be in that zone for any given earthquake. They do not yet know what determines whether a reflected pulse triggers slip or passes through without consequence. Park's own words in the published paper, this is adding an entirely new angle of seismic hazard scientists did not know about before. That sentence is not rhetorical. It is a precise description of a gap in the science. Here's the piece that makes this discovery particularly unsettling. Because detecting this phenomenon requires an extraordinarily dense GPS monitoring network, hundreds of stations distributed across thousands of miles of territory, all operating simultaneously with millisecond precision. Researchers now suspect it may have occurred in other major earthquakes without anyone ever noticing. The 1960 Chile earthquake, magnitude 9.5, the largest earthquake ever recorded by modern instruments. Chile did not have Japan's GPS infrastructure in 1960. It barely had seismometers by modern standards. The 2004 Sumatra earthquake, magnitude 9.1, the earthquake that triggered the Indian Ocean tsunami and killed 227,000 people across 14 countries. Sumatra did not have Japan's GPS infrastructure in 2004. Scientists now believe core reflected pulses may have occurred in both events, and possibly in every major earthquake above magnitude 9 in the historical record, hidden in the data, or absent from the data, because the instruments to detect them did not exist. How many times has an entire country shifted 6 millimeters 15 minutes after an earthquake without a single instrument in range to record it? The answer is, we do not know, and we cannot know. The data from those events is locked in the geological record, not the seismological one. What we can know going forward is different. Japan's GPS network proved that this is real. Park's paper established the physical mechanism. Every major earthquake monitoring agency in the world now has a confirmed phenomenon to watch for, model for, and build into their response protocols. But building it in takes time. Updating risk models takes time. Revising emergency management frameworks takes time. Installing the kind of GPS density that Japan has in regions that do not currently have, it takes years and substantial investment. And the next magnitude, 9 earthquake, the next Cascadia subduction zone rupture off the Pacific Northwest coast, the next major event along the Hikurangi subduction zone in New Zealand, the next great earthquake along any of the dozens of seismically active convergent plate boundaries around the planet, does not wait for the models to update. There is something else in Park's findings that most coverage has not addressed directly, the trigger threshold question. When the core reflected wave arrived at those 4 plate boundaries 15 minutes after Tohoku, it triggered slip, meaning those faults were already close to failure. The reflected wave provided the additional stress needed to push them over the threshold. In seismology, this is called dynamic triggering. It is not a new concept. Surface waves from large earthquakes have been documented triggering distant earthquakes for decades. The 1992 Landers earthquake in California triggered small earthquakes as far away as Yellowstone. What is new is the source. Core reflected body waves arriving at specific distances with specific amplitude, a mechanism that operates on a completely different geometry than surface wave triggering, reaching faults that surface waves might never reach with sufficient energy. This means the hazard is not uniform. It is not a simple ring expanding outward from the epicenter. It is a complex three-dimensional pattern determined by the depth of the rupture, the angle of reflection off the core mantle boundary, and the velocity structure of the mantle through which the wave travels on its return. That pattern is calculable, but only after the fact, with the kind of dense seismic and GPS data that exists in Japan and in very few other places. The Cascadia subduction zone sits off the coast of Oregon and Washington. It is capable of producing a magnitude 9 or greater earthquake. The last time it ruptured fully was January 26, 1700, 326 years ago. Scientists know this not from historical records in the Pacific Northwest, which was sparsely populated at the time, but from Japanese tsunami records and from the geological signature left in coastal marshes. When Cascadia ruptures again, and it will, the question is only when, a core reflected pulse will almost certainly be generated. The wave will travel down through the mantle, strike the core mantle boundary roughly 1,800 miles below the surface, and return to the surface approximately 15 minutes later, where it arrives, which faults it strikes, whether those faults are close enough to failure to trigger. Those are the questions that Park's research has made it possible to begin asking. They were not questions anyone was asking. Before March 11th, 2011 sat in the data for 15 years waiting for someone who would not let the anomaly go. The Tohoku earthquake is one of the most studied seismic events in history. Hundreds of research papers, thousands of instrument readings, terabytes of GPS data, and buried inside that data, hidden in plain sight for 15 years, was the first confirmed evidence of a phenomenon that changes the definition of what an earthquake does. Not just the fault rupture, not just the surface waves, not just the tsunami. The earthquake also sends a pulse downward into the earth, bounces it off a boundary 3,600 miles away, and delivers a second event to the surface 15 minutes later, with enough energy to trigger 4 separate plate boundaries and move a country. Here is the sentence that closes every loop opened in this video. The hazard is not what we thought it was. The shaking stopping is not the all clear. 15 minutes after the largest earthquakes in human history, something has been happening that we had no model for, no protocol for, and no instrument network dense enough to detect, until Japan built one and a geophysicist in Chicago refused to file the anomaly away. The science will update, the models will update, the risk frameworks will update, but those updates require the will to treat a 15-year-old GPS anomaly as the most important data point in modern seismology. Park did that. The question is whether the institutions that build earthquake warning systems, design evacuation protocols, and engineer critical infrastructure in seismically active regions will do the same before the next magnitude 9 event delivers a second shockwave to a population that has never been told one was coming. If this video changed the way you think about what an earthquake actually is, not just the rupture, not just the shaking, but the full sequence of what that energy does for the next 15 minutes, share it. The people who need to understand this are not only the ones already watching geology channels, they are the ones who live near subduction zones and have never heard the words core reflected pulse. Subscribe if you want to understand what the next event means before the headline tells you it already happened.